Greetings, mathophiles, and welcome to a video on the first derivative test, which is a result in calculus that allows us to identify locations of relative maximum and minimum values of functions. This is related to some work we did in another video on increasing and decreasing functions, and I'll place a link to that in the video description here. There'll also be a future video on examples of how to apply the first derivative test, and once that is uploaded, I will place a link to that in this description as well. We should begin by saying what it is we mean by relative maximum and relative minimum values of a function. And so you will see those definitions on the screen. A function f is said to have a relative maximum at some value x naught if there's an open interval containing x naught, such that f of x naught is greater than or equal to f of x for all x in the interval. This does not mean necessarily that there aren't other locations elsewhere where the function might take on a greater value. It just means that in its own little local area, in its own little open interval, x naught produces the maximum value for the function. Similarly, for the minimum, you have a relative minimum at x naught if f of x naught is less than or equal to f of x for all x in some open interval containing x naught. And we have a catch-all term called extremum, which allows us to refer to something that is either a maximum or a minimum. It's kind of handy when you've located a location where there potentially would be a maximum or minimum. You haven't yet decided which of those it is. We're going to begin by taking a look at this function, which is f of x equals x cubed minus 3x. It's a cubic. And we're going to turn on a slidable point, and we're going to make a tangent to the graph of this cubic at that slidable point. And if you've seen the previous video on increasing and decreasing functions, you know that if a function is differentiable somewhere and the derivative is positive, function is going to be increasing and conversely. And same thing for, or similar thing for a decreasing function and a negative derivative, negative tangent line slope. What we're interested in today is what happens at a maximum value or at a minimum value. And of course, one of the things that can happen is that the derivative is zero. In the transition from a positive derivative that we associate with an increasing function to a negative derivative that we associate with a decreasing function, if the function remains differentiable all the way through that process, then it's going to have to be the case that it passes through zero. It's basically an intermediate value theorem argument. Similarly, for a minimum, as we see down here. Now, another thing to consider is the direction of the change in sign. If I'm at a maximum, then I must have been increasing to the left and decreasing to the right. So I must have a positive derivative to the left and negative derivative to the right. And of course, those roles would be reversed if I was at a minimum value. I would have a negative derivative to the left and a positive derivative to the right. Of course, it's possible that a function could have a zero derivative, that is to say a horizontal tangent line, without the derivative having an opposite sign on either side of that value. Here is another cubic, and as you can see, we have a point at which the tangent line is horizontal, and yet there's not a sign change in the first derivative. It's positive both to the left and to the right of this value. And as you can see, if there's no sign change in the first derivative, there need not be, in fact, there can't be a maximum or a minimum at that value. So it's important to take note of this example because people often falsely assume that if the first derivative of a function is zero, the function must therefore have a maximum or a minimum at that location. And this would be a counterexample to that. You need to have the sign change as well in order to see a max or a min. Here is another function. And it has this crazy cuspy little thing with the sharp downward point. And as you can see, of course, there is a minimum there, but there is no derivative there. Our function is not differentiable at x equals 2, and yet clearly there's a minimum. We have a negative first derivative to the left, we have a positive first derivative to the right. So, in fact, you can have a maximum or a minimum at a place where a function is not differentiable. And this would be an instance of that. These three examples strongly suggest the following theorem. Suppose f is a function defined on an open interval containing x naught. If f has a relative extremum, max or min, at x equals x naught, then either f prime of x is 0 or f is not differentiable at x naught. That is to say, the first derivative is undefined. Got to be one of those two things. And this gives us a great way of knowing how to proceed to try to find the locations of relative maximum and minimum values of functions. There's one more thing we should take a look at before we're ready to formally state the first derivative test, and that's a situation in which the function may be discontinuous. So I have an example of that here, and as you can see, we have a situation where we have a negative derivative heading into x equals 3, we have a positive derivative to the right of x equals 3, we have an undefined derivative at x equals 3, and so you would think, based on some of the musings we've made so far, that this would have to be a minimum value of the function at x equals 3, and yet it's not, right? So we're going to have one additional requirement in order for the things that we've been saying about signs of derivatives to work out, and that is that the function has got to be continuous at the location in question. We're now in a position to formally state the first derivative test once we give one additional piece of terminology, and that is the critical value. A critical value is just a value of a function at which the first derivative is 0 or undefined. So these candidate locations for maximum and minimum values of functions are called critical values. The subset of all critical values where the first derivative is 0 sometimes are called stationary values, but you more typically hear critical value used as a catch-all term for all of these kinds of locations. So what's the first derivative test say? It says suppose f is continuous at a critical value x naught. If f prime is positive on some open interval extending to the left from x naught, and f prime is negative on some open interval extending to the right from x naught, then f has a relative maximum at x naught. And if you just do a little reversal, you get the second part. If you have a negative derivative to the left, positive derivative to the right, then you have a minimum. And finally, if the sign of the first derivative does not change across a critical value, then there is neither a maximum nor a minimum at that value. We'll look in a future video at how to apply this. Meanwhile, happy mathing.